This lecture is part 1 of lecture on section 5.2 from Math 311, course in linear algebra at Western Illinois University. The topic is orthogonal complements and projections, and this is part 1, and we're mainly just going to focus on orthogonal complements today. So the idea here is we'll go back to these two examples we looked at earlier, where we take in this case we take two subspaces in R2, which are really just two lines going through the origin that are perpendicular to each other. And I think we were able to see that any vector from this line is going to be orthogonal to a vector in this line. Certainly, if we and you'll notice that this is not necessarily the x and y axis, but in some ways it might as well be. We're going to see that every vector in R2 can be written as a sum of something from this line plus something in this line. Similarly, in R3 we have a plane and a line which are orthogonal to each other. That is, the line hits the plane at a 90-degree angle. And once again, if we take any vector, we're assuming that both these subspaces go through the origin, and we'll also see that every vector in the plane is going to be orthogonal to any vector that's embedded in this line. Okay, and what we see here is what we're actually saying is that these two lines in R2 are orthogonal complements of each other, and here this plane and this line are orthogonal complements to each other. And there we're going to see that the main goal of this section is to show that in any vector in Rn can be written as a sum of two, as a vector in the subspace and its orthogonal complement. Okay, so let's talk about what do we actually mean by orthogonal complements. So throughout this throughout this section, W is going to be a subspace of Rn, and then we define the orthogonal complement of W to be this set, which we denote by W with a perpendicular sign. So sometimes we call this W perp, or in some cases I'll slip and say W dual. But this set is defined to be all the vectors in Rn that are orthogonal to orthogonal to all the vectors in W. That is, all vectors V, such that V dot W is equal to 0 for all little w and big W. Okay. The fancy name is the orthogonal complements. Sometimes we call it the dual of W. Okay, or sometimes I'll just be slip up and say W perp. So the first thing we want to show is that W perp is in fact a subspace of Rn. So we know what to do when we show that something is a subspace. We first note that it's non-empty. Well, we can clearly see that 0, so as for why this is true, 0 is certainly going to be in W perp, because 0 vectors are orthogonal to everything. If let's say V1, V2 is in W perp, and let's say C is a real number, and let's say just little w is an element of big W, what we're just going to show is that V1 plus V2 is orthogonal to W. And why is that? Well, we can just take the dot product, and we can use the distributive property. Okay, and then this is because V1 and V2 are orthogonal to W. This is 0. This is 0, and so the result is 0. Okay, so this means that V1 plus V2 is in W perp. And if we take C1 times CV1 and take the dot product of that with little w, this is c times v1 dot v, c times v1 dot w, which is just going to be c times 0, which is 0. Okay. So we can see that c v1 is also in w perp. So w perp is closed under vector addition and scalar multiplication, and thus it's a subspace. All right. So now that we have that understood, we can talk about, we have this immediate fact here. Well, it's not so immediate, but it looks like it should be simple. It says the orthogonal complement of the orthogonal complement of W is W itself. Now, to show this, we can certainly see that W is contained in here, because if W, let's say if W is in W, and let's say V is in W perp, then, well, actually, we can just say that if little w is in big W, then little w dot x is equal to 0 for all x in W perp. Okay, that's clear. So that would mean that little w is in W perp, and that means that big W is in big W perp. Okay. So that isn't too bad as far as this proof goes, as far as the y goes. However, we still need to show that W perp is contained in W, and we're going to do this later. Later on, actually, it will be in the next video. It looks like it should be easy, but and it will be after we prove something in the next video. Okay, so we'll come back to that. All right. Another property of orthogonal complements is that W and W perp only have one vector in common, and that's 0, the 0 vector. Okay, so why is that? Well, if we take an arbitrary element in this intersection, okay, so it's for the y, if, say, a vector v is in W and in both W perp, let's just take, what is v dot v? What is v dot v? Well, you can, if you think about it for a moment, it has to be 0, because because we're taking v to be in this v is in W, and this v, well, is going to be in W perp. It's obviously the same v, but because this vector, the first vector is in W, the second one is in W perp, they're orthogonal, so this has to be 0. Okay, and so the norm of v is 0. Well, the only way that can happen is if v equals 0. We're using, obviously, this helps the fact that we're working over the real numbers, because this really is just going to be the sum of squares. Okay, and the only way the sum of squares of real numbers can be 0 is if all the squares are 0. Complex numbers, it's a little more difficult, which is a good reason why we're not working over complex numbers right now. All right, so this is going to be important. Another tidbit is to know that to find what the W perp is, we really just need to, we don't have to check that they're orthogonal to every single vector in W, which would be impossible because there are infinitely many. We just need to show that it's orthogonal to all the generators, okay, or all the vectors in its spanning set. So if W is the span of vectors W1 through WK, then V is going to be in W perp if and only if V is orthogonal to each Wi for I going from 1 to K. Okay. And the reason for that, we'll just give it's not going to be a very rigorous proof at all. We just say that let's say if W is if little w is in here, then it's a linear combination of these vectors. Okay, and then if we take the dot product of both sides with V, we can use the linearity of the dot product, and this is going to be C1 V dot W1 plus dot 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 plus C V dot WK. So, so clearly, if we have, if we have this, if this holds, then all these terms are going to be 0, and so this will be 0. This whole thing will be 0, and that will mean V dot W will be 0. Okay, so that will show that that V will be in W perp. Okay, because everything in W can be written in this way. Obviously, if V is already in W perp, then this automatically holds because all of these Wi's are going to be in W. Okay, so we've actually proven both directions. So we just have to show that it's orthogonal to all of its everything in the spanning set. One other tidbit of information before we do an example. Going back to matrices, remember there are 3 main subspaces associated with an n by n matrix. It's row space, it's column space, and it's null space. And if you think about it for a moment, the null space of A is precisely the orthogonal complement of the row space. Now, how can that be when the null space is all vectors V, such that AV equals 0. What do we do when we compute AV? We're really every component of AV is really a dot product of V with a row of A, right? So for this to hold, we're really saying that R dot V is equal to 0 for each row R of A. And because the rows of A generate the row space, from our last result we conclude that this is just the orthogonal complement of the row space of A. Okay, maybe we should just be clear, we're taking the complement of the row A, not A. Okay. Similarly, if we just replace A with A transpose, this now becomes we get this exact A is replaced with A transpose, and of course a row of A transpose is a column of A. So we have that this is all of the null space of A transpose is all vectors V which are orthogonal to each column of A, and each column and the columns of A are just the generating set of the column space. So this is the orthogonal complement of the null space of A transpose. Okay, so that's that kind of what they call the fourth fundamental subspace of A. The row space of A, the column space of A, the null space of A, and the null space of A transpose. And we won't do a specific example here about this because obviously we know how if you can find the null space of A, you can find the null space of A transpose. It's just a different matrix. Okay. All right. So one example I would like to do, or about 3 examples, is how do we actually find these orthogonal complements? Okay. In this first case, we have a line. This is a fancy representation of a line in R2 given by 5x plus 2y equals 0. In this case, we can see that this means that 5x is equal to negative 2y, or negative 5 halves x is equal to y. So we can think about this. This is the span of the vector, and we have, so, a typical element will be in the form of x, negative 5 halves x, or we can, so as the spanning, for a spanning vector, we can just take x to be 1 and negative 5 halves. Okay, and now we just want to find, determine all vectors that's orthogonal to this one vector. Well, I think it's pretty easy to see what that is. We're looking at all vectors, let's say, use some different variables, st. So this is 0. Well, that means that s minus 5 halves t is equal to 0. So we can write s equals 5 halves t, or t is equal to 2/5 s. And so this st is really going to be s 2/5 s right here. So this is a typical element in the dual. So we had, and of course this is just s times 1 2/5 s, or 2/5. Okay. So W perp is really just going to consist of all vectors x, y. I'll just tell it is where y equals 2/5 x. Okay, and when you think about this, it's what it should be. The line 2/5 x and negative 5 halves x are perpendicular to each other. We know from basic algebra. Okay, so there's no surprise there. This is also, we can also write this as a span of 1 and 2/5. Okay, you can give your answer in either way. That's fine. In example 2, we'd like to find what's the orthogonal complement of this plane given by x plus 3y minus 5z equals 0. And in this case, this is almost too easy because we can see that every this right here is in fact the dot product of x, y, z and 1, 3, negative 5. Okay, so we can see that everything here is orthogonal. Everything in W is orthogonal to 1, 3, negative 5, or if you will, 1, 3, negative 5 is going to be orthogonal to everything in W. So we get that W perp is going to be the span of 1, 3, negative 5. And of course that's a line. This is a line, which is actual line when you think about it. It's a line going through the origin given by x equals t, y equals 3t, and z equals negative 5t. Okay. That'll be that line. All right, now let's do something in 4 dimensions. This is going to be a little more difficult, but not too much, right? So what we want in this case, here we have a 2-dimensional subspace in R4, which is generated by these 2 vectors. Okay, so what we're really looking for is we're looking for a vector wxyz that's orthogonal to both of these vectors. So we want this, the dot product of this and 1, 0, 2, negative 1 to be equal to 0. And we want the dot product of wxyz and 3, 1, 1, 4 to be equal to 0. Okay, this is going to correspond to the equation 1 times w plus 0 plus 2y minus z equals 0. And this corresponds to the equation 3w plus x plus y plus 4z equals 0. So we have two equations and 4 unknowns. If we wanted to find write the augmented matrix for this system, this would be 1, 0, 2, -1, and 3, 1, 1, 4. And we could just write plus, a line here and say 0, 0, or what we could just do, in fact, what we've done is it's sufficient just to find the null space of this matrix here. Okay, because in fact what we've done is we're trying to find that we can take W in fact is the row space of this matrix. So the null space of this matrix is going to be the orthogonal complement of the row space. All right, so we just need to find the null space of this matrix using our good friend reduced row echelon form and Gaussian elimination. And there you can see there's not much to do here, is there? We just have to multiply this first row by -3 and add it to the second row. So this is 1, 0, 2, -1. And so -3 plus 3 is 0. 0 plus 1 is 1. -6 plus 1 is -5. And then +3 plus 4 is 7. Okay, so it's in a reduced row echelon form. So now this is, now we just say that if this corresponds to the variables w, x, y, z, we get that w plus 2y minus z equals 0, which is in fact the same thing we had up here. And down here we get x minus 5y plus 7z equals 0. And this tells us that w can be written as minus 2y minus 2y plus z, and x can be written as 5y minus 7z. X can be just written as, y can be written as 1 times y plus 0 times z, and z can be written as 0y plus 1z. Okay, so we can see that everything is going to be, everything in the null space of this matrix is going to be a linear combination of the vectors -2, 5, 1, 0, and 1, -7, 0, 1. Okay, because this is just y times this vector plus z times this vector is equal to this, right? Okay, so we get that that w perp in fact is going to be the span of these two vectors, and you can check that this is orthogonal to this should be all. You just have to check that these vectors are orthogonal to these vectors, and if we did everything right, like for example, -2 plus 2 is 0, and then we have 1 and -1, that's 0, and then if we take these two, we get -6. -6 plus 5 plus 1, okay, so that's 0, and 3 minus 7 plus 4 is 0. Okay, so this does work. So that's the orthogonal complement. So this last case is really just linear algebra, and in fact, all you can do a lot of these using just once you find the generators, you can just write them down, form a matrix, and find the null space. And that's all for today.